Hello, everyone. My name is Greg Ristabin from Olympus NDT. I'd like to welcome everyone today to this webinar on the new corrosion module for the EPOCH 600 Flaw detector. This webinar will include a presentation on the new features and capabilities of the EPOCH 600 corrosion module, as well as a live demonstration of its functionality. Our presenters today are Coleman Flanagan and Grant Reig. Coleman is a product manager Coleman is a product manager for conventional ultrasonic flaw detectors for Olympus, and Grant is the director of product management. This webinar will last approximately 60 minutes. If you have questions, please type them into the Q&A panel in the lower right portion of your screen. Do not type the questions into the chat panel, as we do not monitor it for Q&A purposes. If we don't get to your questions during the live event, they will be addressed personally either by email or by phone after the event is over. This presentation, along with the Q&A, will be archived on our website at www.olympus-ims.com. Now, without further ado, I'd like to turn the presentation over to Coleman Flanagan. Coleman, it's all yours.
Hello and welcome to the webinar. Today we'll be covering several topics relating to the world of corrosion, and more specifically, how a new and exciting feature on the EPOCH 600 Flaw detector can improve your corrosion inspections. So our webinar today will include the topics you see before you. We'll cover an introduction and an overview of the EPOCH 600 corrosion module features. We also want to review some of our key technology advantages of digital corrosion instrumentation as a general subject. I'd like to give you a live demonstration, or at least as live as a webinar allows, of the EPOCH 600 corrosion module feature. And then I'll pass the presentation over to Grant Reig, who will provide a survey of some current Olympus technological solutions in the corrosion market as again, as a more general topic. So to start off the webinar today, we'd like to talk a little bit about ultrasonic NDT corrosion market trends. So when we talk about the corrosion market, and I should specify, in fact, really we're talking of the corrosion and erosion market, commonly sort of abbreviated as corrosion market. But corrosion and erosion market, historically we've accomplished inspections ultrasonically through two primary methods. The first and most common would be single point measurements. So this is using typically a small handheld instrument to make discrete points and take thickness measurements from these points throughout a whole component or a whole part. And a more sophisticated method historically has been more XY component mapping. So this often involves using a scanner, whether it's a handheld or a motorized scanner encoder, and collects data across 2 dimensions on a component. And this allows sort of a faster collection of data, but certainly it's a higher level of training that's required for this kind of inspection. So both of these approaches have their advantages and have their disadvantages from an application point of view. And a lot of those trade-offs have to do with the amount of time it takes to inspect a part, the required training of the operator or operators that are involved in the inspection, and certainly for the financial people, the amount of money or the investment that's needed for the equipment that's used for these applications. So if we focus a little bit on single point measurement, this is really probably the most popular, the most common type of corrosion measurement made throughout the entire world. And there's several reasons for that. Certainly, the first would be it's a low investment for equipment. Again, typically this is handled with just a small portable electronic device. It doesn't require scanners and acquisition devices and advanced analysis. Often this also requires less operator training. So the more simple the device, the less training is required for an operator before you can send him or her out into the field to collect these data measurements. And it does allow, relatively speaking, fast data collection and balanced with very simple analysis. So it's a very popular method. It's a fairly inexpensive method, but certainly while the discrete data point collection is quick, the overall process tends to be a bit longer because you do need to actually make a measurement from every discrete point that needs analysis. So the trend in the market these days, many service inspection companies and NDT contractors and the quality technicians that are tasked with making these corrosion inspections throughout the world are starting to require more versatility from their ultrasonic equipment. The world economy as it is today, it's the age of doing more with less. So while it's still a very reasonable practice to use a dedicated corrosion gauge, and in fact many companies do as a primary focus of their business. If you're working with a service inspection company that does other ultrasonic applications beyond corrosion, such as flaw detection for welds or cracks or other types of ultrasonic applications, it becomes quite a bit easier if there's one instrument that is able to sort of tackle both types of inspections. So this varying requirement of applications pushes a lot of these service companies towards investing in a single piece of equipment, and it does require often that the personnel operating that equipment need to be trained in multiple techniques. That's one method of using a single piece of equipment for a variety of applications. But we at Olympus have also seen that some inspection companies will purchase equipment, maybe it's at times backup equipment, but it can be used for either flaw detection or corrosion purposes, even though they have a department that's segmented into maybe level 2 operators and level 1 operators, or more corrosion dedicated operators versus flaw detection operators. So the market trend seems to push towards having one consolidated, one instrument that's trying to service both applications. And of course, there's advantages to this. A single instrument purchase certainly lowers the overall investment that a company needs to make to attack a variety of ultrasonic applications. And typically, that single instrument purchase is going to be a flaw detector. Most flaw detectors can also do corrosion measurements, whereas most corrosion gauges are dedicated just for corrosion. They're not able to also do angle beam inspection and other flaw detection applications. But a major disadvantage of using a flaw detector for corrosion markets is the level of training that's required and the level of manual operation of a flaw detector that's required. So control of the pulsar and receiver parameters, even gain adjustment and adjustment of the gates, these kinds of controls and adjustments are often not part of the training for a dedicated corrosion gauge, because they're usually eliminated by this corrosion gauge equipment. So this can highlight a disadvantage of consolidating the applications into one instrument. So based on this very brief survey of market trends, Olympus has developed a software feature for the EPOCH 600 that is specifically targeted towards the corrosion market. And this is what we're here to talk about primarily today. And there's very simple direction for this software feature. The real highlights in the EPOCH 600 corrosion module are to design this feature around simplicity. So all of the disadvantages that we just discussed with using a flaw detector for the corrosion market tend to hinge the disadvantages come from the manual control of a flaw detector, the higher level of training required. So our efforts from Olympus with this corrosion feature are to simplify this overall process both in function, in initial setup of the instrument, and also in the scope of its use. So this feature is intended to hit at the core corrosion applications and markets, not necessarily deal with some of the higher and more sophisticated considerations in the corrosion market, but again, focus on a very simple approach. And of course, the benefit of this is that it's a very minimal investment. The Flaw detector purchase itself helps with the equipment investment because it's a single platform, it's a single instrument that will attack both flaw detection and corrosion applications. And then this software feature added on is another small investment, again, just a software addition to the instrument that allows this simplified approach towards corrosion. So we will, of course, learn a bit more about this as we get into the live demonstration of the instrument itself. But I do want to highlight a couple of the key features that have been developed into this corrosion module, as we're calling it, on the EPOCH 600. Of course, we talked about the simplified user interface, but some of the enhancements, the ultrasonic and algorithmic enhancements to the unit, include things such as automatic gain control. So the operator is no longer required to manually manipulate the gain to optimize the signal height. We've implemented the Olympus thickness gauge detection algorithm, and this means the method that we use to make reproducible and very accurate measurements on the waveform. So this certainly helps compared to standard flaw detector use. And through this corrosion feature, we're also able to add V-path correction for the transducers that are supported on the unit. And we'll talk a little bit more about that V-path correction in our next section. The instrument setup is quite a bit faster. This is something I'll demonstrate for you in just a few minutes. And then to add some value and some enhancement beyond standard flaw detector use, we have some other features like a color-coded grid view, a timed B-scan collection, and our expanded data logger functions such as 2D grids and 3D grids. These are file types that are very common for the corrosion market to lay out surveys and inspection techniques. So these are some of the key features that we'll again highlight a bit more through demonstration today. But before we get to the live demonstration, we wanted to talk just a little bit about some of the advantages of these features and of digital corrosion technology in general. So commonly, the argument for purchasing a dedicated thickness gauge, corrosion gauge, compared to a flaw detector for the corrosion market includes some of the points that you see here. So size and cost is usually a factor. Typically, corrosion gauges are a bit smaller and more portable than a flaw detector, and they are typically less expensive. So this is certainly a plus towards the corrosion gauge sales. The ease of calibration and operation, that's also typically an advantage of the corrosion gauge, the dedicated corrosion gauge. But as we've already started to discuss, this is something we might be able to help out with from a software perspective on a flaw detector. Corrosion gauges typically have auto probe recognition, so they understand once you plug in a dual element probe, the instrument knows what probe is plugged in, and that certainly aids in setup of pulsar and receiver parameters. The V-path correction is usually built in on a corrosion gauge. And there's something called auto zero compensation, or if you've used an Olympus thickness gauge in the past, you'd know that as do zero. So this is something we'll discuss a little bit more in detail. But this certainly helps with initial setup of the measurement on a corrosion gauge. Corrosion instruments usually have greater data logger capacity in terms of file types and also number of thickness points that can be collected. And often a dedicated corrosion gauge will include a simple through paint or through coat measurement algorithm. So usually requires a specific transducer, and it allows through paint measurements of a steel layer or a substrate. The thickness gauges tend to have better thickness accuracy, and this often is the critical point in deciding to purchase a corrosion gauge, dedicated corrosion gauge, compared to a flaw detector, is the amount of accuracy that's required either by the procedure or by the quality manual for the inspection that's underway. And finally, temperature compensation tends to be an issue. This is especially true with boiler tubes and work in refineries. You'll see a lot of elevated temperatures, and the transducers as well as the instruments need to have some level of compensation to handle variations in thickness measurement accuracy for temperature. So if we look at a couple of these advantages in more depth, auto probe recognition is kind of a broad topic, actually. This covers a lot of the concerns that a flaw detector user would have when approaching a corrosion application with a dual probe. The first thing that auto probe recognition gets you, one of the major benefits, is that when the instrument understands what probe is connected, it can automatically make adjustments to the pulsar settings to optimize the way that the instrument is pulsing the transducer, and often that comes that has to do with the known sensitivity of a particular transducer, but also things like the frequency of that transducer. And it also allows optimization of the receiver components of the instrument. So everything from the amplification, the gain that's applied initially to find backwall echoes, as well as filter settings and other components of the receiver. So these things can be automatically set up by knowing what probe is connected, and the operator is no longer required to go in and make those adjustments. Also, by knowing what probe is connected, a VPAP correction can be established. And that's kind of what we're showing here in this diagram. If I get my laser pointer, my faux laser pointer here. Any dual probe, or certainly most dual probes, are constructed with two crystals, a transmit and a receive, that have what we call a roof angle. And due to this roof angle, the sound actually travels through the delay of the dual probe and enters the part at a very small angle, typically just a few degrees. What this does is it actually gives a type of focus to the sound. And for a backwall surface that's pitted or very rough and corroded, very uneven surface, this can actually help quite a bit with sensitivity when the sound reflects more focused off of a small pit and then is received back on the receive channel. However, this change in angle results in a small change in the way that the sound travels through the part and the timing. So if this V path, because it looks like a V, if that's not compensated for, then there will be some small inaccuracy in the thickness measurement, especially over larger thickness ranges. So V-path correction in some cases is a less significant factor, but in some thicker components can be a very significant factor in the accuracy of the corrosion measurement. If we switch now and talk a little bit about the auto zero compensation, or again the do zero function on many of the Olympus gauges, this is a very convenient way to establish the probe delay or the zero offset of your dual transducer before you even go and actually couple to the inspection piece. So we will demonstrate the value of this function again in just a few minutes during the live demonstration. But the idea here is that without coupling to the test piece or to a calibration block, the instrument is actually able to send sound through the delay material on each side of the dual probe and receive sound back from the reflection at this barrier at the end of the delay. And by timing the amount of time it takes for the sound to travel through this delay line, the instrument can actually calculate an approximate zero offset or probe delay for that transducer. Now, of course, it doesn't include the couplant layer, and it doesn't take into effect any surface roughness conditions, but it's quite a large step towards accurate measurements compared to starting from an actual initial pulse zero and having to make a full calibration in order to eliminate any probe delay from the measurement. So this is a really important component of simplifying the setup of a corrosion gauge. Now, the detection algorithm, I mentioned before, Olympus has a very specific way of measuring repeatably and accurately the backwall reflection from a dual transducer. And there's actually two factors involved when we look at the comparison between this automatic thickness gauge detection algorithm and something more standard on a flaw detector. The first has to do with flank detection or edge detection on a flaw detector. So the graphic that you see here indicates a fairly common signal that's returned from a dual transducer from corrosion, and you'll see that there's a gate that's set to approximately maybe 20 or 30% screen height. What's very common in a corrosion inspection with a flaw detector is to make a thickness measurement based on the first crossing point of this echo over the gate. This is a flank detection or an edge detection. Unfortunately, as you're moving across the inspection piece, and certainly when you're dealing with surface roughness, the attenuation of the coupling layer, the presence of the coupling layer, there are a lot of factors that can figure into having this signal strength decrease as you move over the part. And it's very visible in this description, or this illustration, that as your signal amplitude decreases, in this case by 6 dB, the point at which you're going to make a thickness measurement changes drastically. And the distance here between detection 1 and detection 2, in many cases, this could result in an inaccuracy up to 20 thousandths of an inch or half a millimeter, or it could actually even be worse than that. So the flaw detection approach to corrosion gauging with this flank detection for measurement, this can lead to some inaccuracy and requires the operator to be very vigilant about the signal strength that's shown on the display. Likewise, especially in the case of pitting in corrosion applications, it's very common for the signal to have multiple peaks from a single backwall signal. So this is illustrated in this slide here. You can see that in the top case here, we have a peak signal that's maybe 3 or 4 lobes into this waveform. And as you move the transducer over different levels of pitting and surface or backwall roughness, you can actually get a switch in the highest amplitude peak from this overall signal. So if you chose from the previous slide as a flaw detector user, if you chose not to use flank detection and instead to use peak detection, you can still run into inaccuracies due to these switching peaks from the waveform. So again, especially in pitting, peak detection is also not maybe the ideal solution for thickness gauging, and this can cause some inaccuracies. The detection algorithm that we would consider a zero-cross algorithm, or our Olympus thickness gauge detection algorithm, doesn't worry about which peak is being measured or the flank at a certain level. Instead, the way that this works is we set a certain detection threshold. So as long as the signal strength is higher than roughly 15 or 20% screen height, the instrument is going to register an echo as a backwall echo. And then it uses a proprietary algorithm to work backwards on that echo and find the first point where that echo crosses the baseline, or the 0 mark. And it makes the measurement from that 0 cross. And by doing that, we don't need to worry about, or we don't need to worry as much about the signal strength. As long as we have sufficient strength to get over this detection threshold, the instrument is going to make the measurement from the same point on the waveform every single time. So the accuracy here is greatly increased, and the repeatability of the measurements is greatly increased without having the operator worried about signal strength, gate placement, or gate level adjustment. So it's a really important factor in accurate corrosion measurement. So if we return to this slide that I outlined before, common thickness gauge advantages versus a flaw detector, now we can actually start to eliminate some of those advantages. So this corrosion module is enhanced compared to a standard EPOCH flaw detector in some of these areas. Size and cost still may be a consideration for you to purchase a dedicated thickness gauge, but ease of calibration, auto probe recognition, and auto zero compensation, we've made some significant enhancements for the flaw detector with this corrosion feature. With VPath correction, the data logger capability, and the thickness accuracy, we've actually done studies internally to compare this feature to our corrosion gauge line, and we find that there's virtually no difference between the corrosion gauge and the thickness gauge on these points that you see here highlighted in green. So in this case, the performance, as a reference, we look at our 38DL Plus corrosion gauge, the performance is virtually identical. So it's a really significant enhancement compared to what you would get from a standard EPOCH 600 using more traditional methods. So that's a lot of talking to describe what we're going to do with this feature. But now what I'd actually like to do is switch over to a live instrument and provide a bit of demonstration on what we can do. So we'll just bear with me here for a second while I switch over to the live unit. And now you can see here the EPOCH 600 screen. So we have the instrument right now. I have this set up in flaw detector mode. So this is your standard EPOCH 600 flaw detector. And what I'd like to do very quickly as I can, is set the instrument up in a manual mode, in a flaw detector mode for a simple corrosion application. So some of the common steps, the first thing we'll want to do is make sure that our velocity is approximately correct for steel, which it is here at 5,900 meters per second. We'll turn off any zero compensation right now so that we don't miss any reflections. The range is set fairly well. It's probably too much, but we'll go back and adjust this later. If I go to my pulsar settings, I need to go through these settings and optimize the pulsar for use with the transducer that I have connected. And today I'm going to be using our D790 SM transducer. It's a 5 megahertz dual probe. And so what I'm going to do is adjust my energy up to, let's say, 300 volts just for optimum penetration. I need to make sure to switch the mode from pulse echo to dual. And this actually is a very common support call that we get here at Olympus from our flaw detector users, people forgetting to switch the mode to dual when they plug in a dual probe. We also will look at our square wave pulsar setting, and we'd like to optimize the width of the pulse for our 5 megahertz probe, which is actually the default setting for this unit. So that's already optimized. Now we'll go to the receiver settings, and we'll select a filter, and in this case I'll actually switch down to a slightly more narrow band filter, 1.5 to 8.5 megahertz. So we've set up our filter. And as I discussed before, another setting that we're going to want to change, in this case we'll set up for flank detection, for edge detection. So if I go to my gate setup, I can change my gate mode to edge detect. And I'll need to boost up my gain quite a bit so I can start to see a signal. So when I couple down to a 12.5 millimeter step on my test block, what I'd like to do is bring the amplitude of the signal up really very high. And I'm going to reposition my gate level a little bit so I don't get caught up in some of that crosstalk that you see. The reason that I'm bringing the amplitude, the gain, way up is so that I have a nice flat leading edge of my echo. And that's very helpful when I'm using edge detection or flank detection. I can see here that I have really too much range, so I'll bring my range down to 50 millimeters, so I'm not looking quite so far out in the echo window. And now I'm at least in the position to start making measurements. Unfortunately, because I didn't add any zero compensation, you'll see that my measurement is pretty far off the mark. I'm measuring almost 34 millimeters. I should be measuring 12.5. So this is the point where I need to go back to my main menu and actually do a 2-point calibration of the instrument, and this will allow me to make more accurate measurements. So we'll do calibration on the thicker step that I'm using today, down to 12.5, continue, and now I'll couple to my 5 millimeter step. And I need to make sure that my gate is not getting tripped up on this little bit of crosstalk, but it's not at the moment, so this is good. And we'll go and set this to, this is our 5 millimeter step, and press done. So now if I bring my range down a little bit and reposition my gate, I should be able to make fairly accurate measurements. So just about 5, slightly below, this should be 7.5, but we're just slightly below 7.5. This should be 10, but it's just slightly below 10, and right about 12.5. One of it could just be that I need to recalibrate a bit to be a bit more accurate with my my coupling. But one of the reasons that I may have some inaccuracy on something like this step, where I'm 0.04 millimeters away from my target, could actually be just the signal height and the position at which I'm making the measurement on the leading edge of this signal. But I think certainly you can see that this took maybe a couple of minutes to set up, and as I go across the sample here, I have a sample with actual corrosion. I can look at this sample, I can make fairly accurate measurements, but I always need to be very mindful of signals that occur before the leading edge of the back wall. I can visually identify that as a back wall. But if I had my gate level set maybe just a little bit lower, you can see now that I'm actually triggering off of some crosstalk effect and not the actual signal in some cases. So as an operator, I need to be very cautious of where my gate is placed and what signal I'm actually making a measurement from before I decide that I can save that measurement as an accurate corrosion measurement. So it's absolutely possible to use a flaw detector as a corrosion gauge and get fairly repeatable and reproducible and accurate results. However, the amount of setup and the amount of continued vigilance by the operator is fairly high for a standard operating mode. If instead I switch the instrument over, so I'll go to my instrument setup general menu, because I'm going to change the mode of the instrument from flaw detector to corrosion gauge, so I'll turn this on. Now you'll get an impression of exactly how powerful this can be and how simple. So I turn on my corrosion gauge. It brings me immediately to a transducer setup menu. The flaw detector has not been modified in such a way that it will automatically recognize a probe when it's connected. That requires additional components on the probe side and hardware on the flaw detector side to make that communication. But we've simplified your initial setup menu, where all you need to do is select the probe that you're using, either a D790 or a D798. And you can see on the right side that it's, by selecting one of these probes, it will automatically populate some important initial parameters, such as the frequency of the probe, the filter, etc. So I'm going to highlight my D790, that's what I'm using today. And when I escape out of this menu, the instrument asks me to wipe the coupling off of my probe and press continue. This is the step where I'm automatically compensating for the zero offset or the probe delay through the delay line of my dual probe. So with the single press of a button, I've optimized my pulsar and receiver settings, my gain setting, my gate position, and I've compensated for probe delay, and I'm now automatically making measurements that are very close to correct. So 5.09, 7.56. They're still a little bit off. We're seeing about as much measurement and accuracy here, maybe just a little bit more, than we saw in the more traditional flaw detector mode. But we haven't done a 2-point calibration yet. So I've already really enhanced my feature set compared to a flaw detector. Let me bring my range down a little bit. Now it's possible, the exact same way I just did on my flaw detector mode, to do a 2-point calibration. So I'll go back to my AutoCal menu as usual. I will put in the actual measurements that I'm expecting to get, 12.5 on the thicker step, and 5 millimeters on the thinner step. And now I should have a very accurate representation of the thickness of this step block. And if I go ahead and I start looking at an actual corroded sample, you can see that on the bottom here we have a little measurement caret that shows me where I'm making my actual measurement. The gate level is not required for the operator to manipulate. This is not something that an operator needs to worry about anymore because we're using the threshold and zero cross detection algorithm. So this really enhances the life of the operator quite a bit, and you can make fast and repeatable measurements. You can review the pulsar settings, but from this menu you can't actually make adjustments. If you prefer to look at this in an RF mode instead of a full wave, you can do that. We'll put it back to full for now. So the basic simplicity already provides a tremendous amount of value for this feature. Now beyond that, we have other capabilities. So if I go back and look at a signal such as my 7.5 step, I can actually turn on gate 2, and I can make an automatic gate-to-gate measurement using the same zero cross detection algorithm, the same automatic gain. You see from my gain up on the top right hand corner, I'm automatically compensating for gain. So thickness or echo-to-echo measurements are possible with basically the click of a button. And as we discussed earlier, there's some extra features that are very helpful in the corrosion market. So something like a color-coded grid. If we go into this grid mode, we turn this on, select a color mode, and we can set some limits here. So anything below, let's say, 5 millimeters, we're going to show in red. Anything above, let's say, 7 millimeters, will show in green. So we can set some thresholds. And I already had a file set up, so I have some data that's already been collected. But now we can go ahead. On the bottom of the screen here, you see a color-coded representation of a 2D grid file. You have columns A through D, and in this case, rows, I believe, 0, 1 through 10. And we can use these arrow keys on the bottom to explore through our grid file and look at the measurements that have already been collected. And if we get down far enough, we'll find some areas where there's no measurement collected. So I can simply highlight that, couple down to my part, and press the Save key, and it will populate a measurement right there. So it's a really simple approach to being able to visualize your data and visualize this in a color-coded method. And in fact, if you start to collect this data and you want to change the threshold, the limits on your colors, you can go back in and make a live adjustment to that very simply. So that concludes our live demonstration for today. Certainly, there are some additional features. We didn't really get into the B-scan. I don't have a tremendous amount of time today, so the B-scan is much more of a peripheral feature on this unit. It's really meant for some basic reporting. So if you find a neighborhood of corrosion and you want to collect a basic image of what that area on your part looks like, it's good to use the B-scan. But it's not an encoded B-scan, so it's not really intended for large sections of a pipe or a pressure vessel. and large collection of data. But hopefully from this very brief demonstration that you've seen today, you can see that there's really two primary benefits. Without getting into all the details that I've shown you, some of the primary benefits, again, I'll stress the simplified operation of the unit. It took me drastically less time to set up the pulsar and receiver parameters and to begin making fairly accurate measurements with a D790 using this corrosion module compared to manually adjusting everything on the flaw detector side. And this could be really critical not only in efficiency of your inspection, but also in the ability of operators to actually use this feature. Again, you know, a very common phone call that we get to our support people, our applications people here at Olympus, are from corrosion inspectors who are used to using a dedicated corrosion gauge. And when they arrived at the office that morning, the corrosion gauges were all out and they were handed a flaw detector and said, go do your work with a flaw detector. And they don't know what a gate is. They are not used to making manual gain adjustment. There's a lot of things that go into using a flaw detector that you wouldn't necessarily be trained on as a dedicated corrosion operator. So this simple feature really allows those types of users to be able to pick up the instrument and make a quality inspection very, very quickly. And of course, that not only increases the throughput for your corrosion applications, it decreases the amount of investment required for the equipment that you'll be purchasing, and it really allows a wide variety of operator levels to use the same piece of equipment and still get the high quality of inspections. So now I'm going to hand the microphone over to Grant Rieg, and Grant's going to provide a little bit of a higher level overview of the corrosion market and the scope of solutions that can be provided. Today we focused in on just one, sort of our latest solution for the corrosion market, but certainly Olympus has a lot more to offer within the corrosion world. So for that overview, I'm going to pass the microphone over to Grant Rieg.
Okay, thanks, Coleman. So as he said, I'm going to review a little bit more a high level of the corrosion market and touch on a few of the other types of solutions and the advantages or disadvantages of some of those solutions as they relate to corrosion itself. So when we talk about corrosion, oftentimes the petroleum industry is brought up. That's a big industry where corrosion is prevalent and it's a major issue. This corrosion can be found in many parts of the value chain. So this can be in the early stages where we're drilling production flow. You can also find it in midstream where you're in production gathering, piping, and also all the way downstream when you're talking refining and at the plant or storage facilities themselves. And this corrosion can actually be caused not only by the products themselves, but much of the support equipment that's used within supporting those functions within the industry. Outside of petroleum, corrosion is certainly prevalent as well. Pulp and paper is a good example where you can find corrosion anywhere within the tanks, the piping, pressure vessels that are used. Marine applications where you find tankers and barge hulls. I mean, it's really common in a very, very wide variety of applications, all the way down to basic water pipes. You might find metal water pipes that have corrosion and need to be monitored. So when we talked about corrosion, there's many different types or really causes of those corrosion. The more common ones you'll find are general wall loss, where you basically have a thinning of a pressure boundary due to uniform corrosion. So a steam line, for instance, in a power generation plant would be a common way you'd find general wall loss. So the corrosion is going to be fairly even, so where you might make one measurement and then 3 or 4 inches down, the measurement will be very similar along there. However, you can also find instances of corrosion where you'll find isolated cells. And this is more common where you see, for instance, where water might separate from a process fluid, and that water might pool in a particular spot, and that would result in concentrated or uneven corrosion in a specific area. Similarly, flow-accelerated type corrosion, where the product itself is abrasive. It essentially acts as a sandpaper and is sanding the pipe from the inside out, and is often found that you're gonna find these isolated type corrosion, especially where there's some sort of focal point or some sort of bend in a pipe, something like that. There's a number of other corrosion listed on this slide here. I'm not going to go through each one individually, but oftentimes they relate to either the product that might be flowing through a pipe or stored in a tank. It can often be related to the geometry of something or how something is assembled, an impingement point, for instance, or a mixing point. So there's many different reasons why we see the corrosion, but what I'd like to really talk about is what the different solutions are that are available to address these different. So there's a number of different, like I said, ways the corrosion is created. We have a lot of different customers that are tackling corrosion, and we really offer a number of different solutions based around these corrosion issues. Now, the solutions that are provided aren't necessarily unique to what has caused the corrosion as much as they are to what we're looking for. So, for instance, if we're looking for point measurements or if we're looking for a more complete mapping system, we might select different products. And that, regardless of whether it's general corrosion or whether it was caused due to an isolated cell or a flow-accelerated section of piping, these solutions can still be used throughout those. So, Coleman had mentioned earlier, so if we start looking at these solutions and sort of start from the bottom here, the corrosion, a dedicated corrosion instrument is one of the lower cost single point type instruments that can be used. And this is very much what Coleman is emulating with the Flaw detector that he's just done a demonstration on. These products are very accurate at reading corrosion. They are a single point measurement unit, however, and they can be oftentimes very simple to use. The waveform on some of these instruments can be optional, so you're in some cases just looking at the thickness reading and only the thickness reading. There's additional software features available to allow you to look through coatings, so painted pipes, for instance, where you want to ignore that paint layer on the top. Temperature compensation, there's a number of different advanced software features that, despite the fact that these are low cost, relatively low investment from a training perspective instruments, they are very powerful for measuring point measurements on corrosion. So these types of instruments are generally used more in those general wall loss or where you want to know a specific point, thickness reading at that point. We do offer corrosion solutions within our Flaw detectors, as Coleman has obviously just demonstrated. There are some thickness gauges that can take advantage of what we call a B-scan buggy. So that's this little wheeled cart that you see here on the left side image. Essentially what this allows you to do is to record position information along with the thickness reading on the transducer. So this buggy would drive down the length of the pipe or be pushed down the length of a pipe, and it will report back to the Flaw detector not only the ultrasonic data via the transducer, but also the position information along the length of the pipe. So it does give you essentially stripe measurements of your pipe, and you can get a profile of that section of pipe to give you an idea of what level of corrosion you're dealing with. Now, if you have a pipe that might have some sediment in the bottom, oftentimes this buggy might be run along the lower portion of the pipe to give you an idea of where it might be the thinnest. There are also B-scan solutions which are not necessarily encoded. So on some Flaw detectors or other instruments, you can just do what we call a time-based B-scan. So this would allow you to just push the buggy along at a uniform pace, and it will record the thickness information and plot it along a B-scan. However, if you do vary the rate of speed of the buggy, it can complicate the measurements due to the fact that it's not necessarily correlated accurately with the position information. Moving from there, you can get into more sophisticated solutions where you can provide much more thorough mapping of an area. So this is an example of a semi-automated mapping system, oftentimes now using phased array instead of a conventional dual element transducer. And we're using some sort of scanner to hold that phased array probe. So we have a chain scanner in this photo here in this application example. In this chain scanner, just like in the B-scan example where it's recording position information along the length of the pipe, the chain scanner is now a 2-axis encoding device. So it's reporting back to the instrument and correlating the thickness data along 2 axes. And it allows you to essentially draw what you see on the screen there, which is called a C-scan. And this draws a map of your part, a swath of area that you wanted to cover. And so if you have an isolated area where you're concerned that the corrosion might be very much different from one point to a next 3 inches over, this allows you to be very, very thorough with the mapping of that particular area and get a full 100% coverage of that. This particular chain scanner will allow you to wrap around the pipe, so we will essentially flatten it and draw a C-scan map around the circumference of the pipe in roughly a 2-foot wide swath. From there, we have a newer system that's available. There's what we call guided wave systems. Now, guided wave is really more of a screening technology, but it is significantly more powerful in the area that it can cover, and it has some distinct advantages over some of the other products that we've already covered, in the sense that it uses ultrasound still. However, what it does is it transmits ultrasound down the length of the pipe. And it has a pretty good reach as far as how far down the pipe, so to speak, it can see. Now, it is impacted by bends in the pipe, so the most ideal case would be a nice, long, straight pipe. But the advantage to this system is that the pipe can be buried. It might be hard to access the pipe, whether it be a vertical pipe that's going up the side of a silo or a building. It will also allow you to ignore any sort of coatings or buried pipes. So if the pipe is buried, it will give you a rough screening of how much corrosion might be present and how far down the length of the pipe. Now, is the tool perfect? No, it's not going to provide the same level of information as if you had gone utilizing an ultrasonic point thickness measurement or a C-scan instrument to do an area of pipe. But it allows you to get a pretty good indication if there's any massive corrosion along the length of the pipe and whether or not it's necessary to investigate further with either a point measurement system or something more sophisticated. So to summarize a little bit, there's the corrosion measurement market and really the issues that corrosion raises is enormous. It's prevalent in not only, like we said, the petrochemical industry, but in many, many different industries. And the level of products to support these solutions is also very great. So what we've seen is with our service company inspection customers in particular, there's often towards this movement, as Coleman mentioned, of consolidation of equipment. And really what that refers to is, like Coleman said, getting more products to do more, or the same products that you have to do more. And oftentimes, while a flaw detector isn't necessarily the most ideal corrosion measurement solution, it's often what a customer might own, and it's what they have. So while they might have a choice to buy either a dedicated corrosion thickness gauge or a flaw detector, they might choose the flaw detector simply for the fact that it's more versatile down the road in the event that they wanted to do additional applications. The EPOCH 600 corrosion module, what we allow there is for a small increase in price, you're getting essentially all of the benefits that you get out of a dedicated corrosion gauge while still retaining that ability to do those other applications that a conventional flaw detector will be able to tackle down the road. So it improves the versatility. If you have users or operators that are not necessarily as well versed in flaw detection and maybe they want to grow into that down the road, the corrosion module, as you've seen, can really greatly increase the learning or decrease the learning curve and allow more simple operation to get a user up and running more rapidly. So that concludes our webinar here for the corrosion module. I'll turn it back over to you, Greg.
Thank you, Grant, and thank you, Coleman. Thank you both for your participation in today's event. Thanks much to all the attendees for joining us. We hope this material was informative and useful. The webinar will be archived on our website at www.olympus-ims.com. Please visit the website for the latest information on all Olympus NDT instruments and applications. That's going to do it for today. All the questions that were asked will be answered individually after the webinar is over. Thank you very much, and we'll see you next time.